Hello everyone, and welcome to Continuing the Math with Mickey. Now, in the previous video, we discussed the very first numerical method ever discovered to be Euler method. And now I'm going to show you the more efficient method of using numerical methods to try to solve a differential equation. That method is Runge-Kutta of the fourth order method. That method was discovered by two mathematicians, German mathematicians, Karl Runge and Martin Wilhelm Kutta. I guess how it goes in Germany 200 years ago, they were just bored and they decided to be mathematicians. And when they became that, they decided to look more into numerical methods, and they did. When they looked at the Taylor expansion for a function, they looked at the very fourth derivative, and they came up with essentially 5 equations with 13 unknowns. They decided to use weight. You remember how in the Euler's method, you just used a single derivative to try to approximate the next value of y, of the function of y, depending on the previous value of y. Now, Runge and Kutta decided to do the same, but they decided to optimize it a little bit by adding weights. And you can see here we have another formula, which still resembles our formula from the Euler's method with here. So we're trying to approximate our new value of y with our previous value of y by adding a set of weights, by also multiplying it by the h, as you saw in the Euler's method. Now, how do we find those weights? Those weights can be found through here. Through our function with which you are working with, can be found through here. Through our function with which you are working with, which is still of the form of dy dx to be equal to just a function of x and y. Now, without further ado, let's try to do an example. Remember how it was pretty fast? Well, fast is relatively speaking. How it was pretty fast for us to try to find the next values of y. You'll see how a bit lengthy it can be for the Runge-Kutta method. Now we have our example with y prime to be equal to 2x times y. We have our initial condition of y1 equal 1. We have our step, and we have our question. What is the function of y at 1.5? Now let's try to find it. We know our initial x's and y's. X of naught is just 1, and y of naught is just 1 as well. In order to find our next value of y, we need to find all of our weights. K1, K2, K3, K4. Let's find them. Our K1 is given by the formula to be just f of x naught, y naught. What is our function? 2 times x times y. So we just plug it in. So it's 2 times our x naught to be 1 and our y naught to be 1. So just 2. Pretty easy. Now K2 is where it gets a little bit complicated. We get our function of x naught plus h over 2 and our y naught plus h over 2 now times K1. Interesting feature how the next weight, K2, is dependent on our previous weight, K1, from here. If we plug in our values, what do we get? We get our still 2. Now our x changes. So we have 1 plus h over 2. We know our h is 0.1 divided by 2 times our updated y, which is still 1 plus 0.1 divided by 2 times our 2, which comes from here for K1. K1, and then comes here K1. When we calculate all of that, we get our new value for K2 to be 2.31. Let's calculate K3. K3 resembles K2. It's our function of x naught plus h over 2, and then function of y. But now look, we get h over 2 times K2 now. our previous weight. So if we do that, we do 2 times 1 plus 0.1 divided by 2, and then 1 plus 0.1 divided by 2, but now times 2.31. Which if we do, we get approximately value of 2.3425. It's actually an exact value. Let me read this. Yes. We found K3, now let's find K4. Changes a little bit, we get x naught plus h. And our y becomes y naught plus h times K3, as we would expect by this point. When we plug everything in, we get 1 plus 0.1 times 1 plus 0.1 times 2.34255. When we calculate all that, we get the value to be approximately 2.7154. Good. Now, we know our weights, and we're able to find our next value of y, which is our previous value of y plus our step. Now, let me just, step over 6, k1 plus 2k2 plus 2k3 plus k4. Which is, we know our y naught is 1 plus 0.1 over 6 times 2 plus 2 times 2.31 plus 2 times 2.343 approximately at this point, and then plus our last value, 2.7154. That whole thing equals to 1.234. Fantastic. Now, as in the Euler's method, let's also try to be consistent and not confuse ourselves. Let's just make a little table. We have our x, we have our y. We know x at 1 is 1. But x at negative x, remember from the Euler's method, x2 is just, x1 is just x naught plus our step. We know our step is 0.1, so we know our next value of x is just 1.1. And for that value of x equals 1.1, we get our approximated value for y to be 1.234. Good. We're one step closer to the answer. Now, how would we find the next value of y? The next value of y, of course, is going to be dependent on our previous values of y. How do we do that? We go back to our calculating again our new weight. Now, weights, as we see K1, K2, K3, K4, don't stay static. They depend on your x and y. For our first iteration, our x and y were 1 and 1. But now, we have our new x and y to be 1.1 and 1.234 approximately. So we use those values to calculate our new weights. Let's do that. For K1, remember, it's f of x1, y1. And that is 2 times 1.1 times 1.234. We get the value to be approximately 2.7141. For K2, it changes a bit as well. We get f of x1 plus h over 2, comma x y1 plus h k1 over 2, which is just 2 times 1.1 plus 0.1 over 2 times 1.234 plus 0.1 divided by 2 times 2.7141. That is approximately 3.1496. Then you do the same thing for K3 and K4. K3 approximately equals to 3.1997, and then K4 equals to 3.7287. We know our new values of K, so we can find our next value of Y. So our Y2 equals again to Y1 plus H over 6. Our updated case so let's use those. So we know that our previous value was 1.234 plus our still value of H is 0.1 over 6. We know our K1 2.7141 plus 2 times our value of K2, 3.1496 plus 2 times 3.1997 plus our fourth K. When we plug it into a calculator, we get our new value of Y to be 1.5527. 1.5527. Now, look at how lengthy the process is. It can be a bit boring, but it's for sure a procedure, essentially. Now, in another video, I do show you how to reduce this process to less than 5 minutes doing it in Excel. Because Excel is known to be one of the tools that can just iterate for you many, many times and very fast. But that's the matter for another video. Now, if you continue doing this process, you will get to the final answer. Now, I'll just give you the final answer here. So we get 1.3, 1.4, and 1.5. And we get the values 1.9937, 2.6116, and then 3.4902. But how do we know also that this method is so much better than Euler's method? We just check. Now we see we have our differential equation y prime equals 2xy. By this point, you should be able to actually solve that differential equation exactly. Remembering the module 2 material, you will be able to actually solve this. When you do, you get the function of y to be with our initial conditions, given that y of 1 equals 1, is e to the x squared minus 1. And when you plug in our x to be 1.5, you get the approximate value of 3.4903. Look how these values are almost exactly the same, except for the not even 1,000. What is it? 10th, 100,000? Yeah, 10th of a 1,000th of a decimal difference. Now that's a pretty good approximation for me, at least for the 5 steps that you're taking. And this is essentially an example of how to do Runge-Kutta of the 4th order method. It's pretty amazing. Now that concludes our review or the studying of the Runge-Kutta of the 4th order. Thank you.